Hey guys, today let's solve the insert into a binary subtree. So this is the given problem, right? They are giving us the root node of a binary subtree and a value to insert into the tree, right? What we need to do is return the root after the insertion, okay? And they are guarantee us that the new value does not exist in the original BST. There are so many ways, right, to insertion as long as the tree remain as a BST after insertion. We can just simply return any of them, right? Let's take a look at the example 1. Let's say the given input is like this and we want to insert 5. How we can do that? Well, first we're gonna check, is 5 bigger than 4? Yes, right? So we move to the right side. Well, is 5 bigger than 7? No, right? So we move to the left side. Because 7 doesn't have any child node, right? So we create a new node and insert it into the left side of 7. It will be looks like this after the insertion. And let's take a look at the example 2. Let's say the given input is like this and we want to insert 25, right? First, we need to check, is 25 bigger than 40? No, right? So we move to the left side. Is it 25 bigger than 20? Yes, so we move to the right side. At the right side, we have 30, right? Is 25 bigger than 30? No, so we move to the left side. And because not 30 doesn't have any child node, right? So we just simply insert into the left subtree. It will be looks like this. Let's take a look at the example 3. Let's say the given input is like this and we want to insert 8. So we're gonna check, right? Is 8 bigger than 4? Yes, so we move to the right subtree. Is 8 bigger than 7? Yes, so we move to the right subtree. Because 7 doesn't have any child node, we just simply insert to the right subtree. So after insertion, it will be looks like this. So the main thing that we need to understand, in BST invariant, the left node is smaller than the root and the root is smaller than the right. So we can just simply check if the given value is smaller than the root, we move to the left subtree. If the given value is bigger than the root, we move to the right subtree. And what if the root is null? Well, we will just simply create a new node and return the new node, right? And we need to return the root to maintain the tree structure. So we can solve it using DFS, recursion, or DFS iteration. Well, how? Let me show you. For the DFS recursion, we will check if the root is null, return the new node. If the value is bigger than the root, move to the right subtree. If the value is smaller than the root, move to the left subtree. Else, we will just simply return the root. Let's see this. Let's say the given input is like this. So first, we will call the insertion in BST, not 40. We are starting from the root, right, which is 40. Then the value, right, which is 25. So it will be insertion in BST, the root and the value. Then we check, right, is 25 bigger than 40? False. So we move to the left subtree of not 40. At the left subtree, we have 20, right? So we check, is 25 bigger than 20? False. Move to the right sub. Is it 25 bigger than 20? That is true. So move to the right subtree of nodes 20, and we have 30 right at here. Is 25 bigger than 30? False. So we move to the left subtree of nodes 30, which is node 30 doesn't have any child node, right? So we create a new node. It will be nodes 30.leaf as the new tree node of the 25. So we just simply return the root. I will copy this, or I will just type it. It will be 40, 20, 30, 60. Then on the second level we have 40, 10, 30, 50, 70. Then now 25, now and now. Okay, it will be just like this, right? Let's turn them into code. Insertion in BST, root value. If the root is null, return new tree node of value. If the value is bigger than root, move to right subtree. Else if value is smaller than root, move to left subtree. Root.right is insertion in BST. We call the right subtree, right, and the value. It will be same for this. The only difference is this one is the left subtree. Left. Okay, then we need to return the root. Let's do the time and space complexity analysis. This one will be all of n time and or this one is for balance tree or n time for unbalanced tree or skew tree. Meanwhile, for the recursion, it will be on space due to recursion using stack. I will just copy this and space due to recursion using stack. Okay, let's move to option 2. First, it will be same if the root is empty, return new node of the value. Then treat current node as pointer. While current node is not null, we need to return the root. Then if the value is bigger than the current node, move to the right subtree. If the value is smaller than current node, move to the left subtree. Else, we need to exit the while loop when the value is equal to current node. Let's say the given input is like this. I will just delete this. So at first, the current node will start from the root, right? It will be node 4. Then while the current node is not null, is 8 bigger than 4, that is true. So we move to the right subtree of not 4, which is 7, right? So is 8 bigger than 7? That is also true. Move to the right subtree of not 7. And because 7 doesn't have any child not, we just simply insert them. Not 7 but right is new 3 not of 8. Then we just simply return the root. It will be 4, 2, 7, 1, 3, null, and 8. Okay, let's turn them into row. Once insertion in BSD root value. If the root is empty, return new 3 not value, or we can just simply create a const new not is new 3 not value, right? Then this one will be return new not. We're gonna use current let for the current not. While current not is not null, if the value is bigger than current not dot far, move to the right subtree. Then else if value is smaller than current not dot far, move to the left subtree. Else handle case where the value is equal to the current not dot file. Then we need to return the root. This one will be big. If the right node is null, right, we will just simply insert them. So it will be current node dot right is new node. Move as deep as possible to the right until it's null for insertion. Current node is current node dot right. I will copy this. Left current node dot left, then we will just simply insert. Okay, move as far as possible to the left until it's null for the insertion. I think like that's all. Let's do the time and space complexity analysis. This one is all one space because we don't need any extra space, right? Meanwhile for this, it will be the same with this. Okay. This one is all one space. Let's try them right into here. Option 1, if as recursion, it will be if the root is null, we return new 3 not and the value. Am I doing something? Or root.file, root.file. Okay, let's try to submit. Okay, it's working, right? Let's see the option 2. If s iteration const new node is new node file, then if the root is now new no, let call node from the root to take the node and s pointer. While current node is not null, if file is bigger than current node value, move to the right subtree. Else if file is smaller than current node file, move to the left subtree. Else we will just break. If the current node right is null, I will just copy this. Okay, let's just submit. I think it is all. See you next time.